So I wanted to talk to you today about a number of topics, and this is not an attempt to ramble or whatever, but I do want to go through several things today. One of them is I want you to become acquainted with a code book, and it's a magazine that comes out, and I want you to become acquainted with that, and I'll share that with you at the end. But we have also want to talk about the some of the stuff. I'm not going to get into the textbook yet. I'm going to talk about some of the stuff that's around the textbook, and we'll just go a little at a time here. Okay, so this is from the one book that I have, which is it's on the Chipman text. This is the book that I told you that was from the guy from the University of Toledo, Chipman. He is dead now, I'm sure, but he was a noted professor of electrical engineering at the University of Toledo. So he wrote a book on waveguides and waves and that type of thing. And before I get into that, I just wanted to tell you just a little bit about one of the things that has to do with uh, waves and transmission of waves and the difference between then and today. So I'll talk to you about that for just a few minutes. So as you're looking through this stuff, you see everything is electrical in here, and that's good, except for the fact that we've gone mainly with fiber in the United States, and that precluded the need for everything to go electrical. So fiber has kind of replaced what you're studying here, and that's one of the reasons why a lot of the stuff that's in these books is a little dated, and it's kind of nice to know about it, but it is not as necessary as it once was. So again, fiber optic cable does not have a wave pattern down it. If you look at a wave pattern that you would like at a lake or something like that, when it gets to the end, what does it do? It bounces back, and that does not happen with fiber, so you don't have to worry about that. So it doesn't. It goes down, and basically that's it. It doesn't have a reflective capability, or it does not reflect back. They don't let it reflect back. So that's one of the things about it that doesn't you don't matter. So again, older cables techniques uh, had to have some kind of a resistor at the end. So you had to hang a resistor across the ends of of your cable. So you would maybe run a cable from, the one room to another, and at the ends you would have to add a resistor of a certain value in order to blunt this reflectivity. And that's not true with the cables that we have today. The Ethernet cables, you don't have to worry about that, those end resistors adding to it. You did before, and those resistors had to be matched to the impedance of the line, or else it wouldn't work. So that resistor had to match the line resistance. So that's an aside about something that you don't have to worry about today, and why, when we use cables um, today, we use what we call UTP, unshielded twisted pair. And why can we do that at high speeds? Because the twist rates are all different. So the twist rates are different for the four pair. So you have four pair in there, but as you look at them, if you take it apart and look at them, they're at a different twist rate. So one would be, they're not shielded from each other, but they're not transmitting so that one can um, overpower another one and leak onto another one. And they only go for 100 meters, 100 meters or less. So you want to run your fiber, and then when you get close, you run with the UTP cable, and that's typically how things are done. Okay, but I wanted to read through some of the stuff that got us to this point, and so some of it is high voltage transmission lines on towers, and they talk about all that and all that power that we transmit when we do that. And we still have those with cell towers, but again, you get to the cell tower with fiber, and then from that point on, you go with the transmission. So you only go fairly short distances with the actual air transmission. Um, um, this talks about the history of electrical transmission, and we sure have gone through a lot of going from one type to the next to the next to the next, and it talks just a little bit about some of that in this article. So he tries to cover the history of transmission rates and getting electrical transmission from one place to another. Okay. Now, his book was on Smith charts, which is one of the ways to, it was the way to figure out how to negate this end error, this end reflectivity. So the Smith chart method was used primarily to not have any reflectivity. So you would basically, I forget exactly how you did it, but you would put a resistor there, or you would clip it off so that there would be no reflectivity back. It wouldn't bounce back. The signal wouldn't bounce back on the wire. So I wanted to just touch base a little bit on the history. Basically, it goes back into the 1800s and even to the 1700s, and talks a little bit about different types of ways that transmissions were done. Okay. Evolution of the electrical transmission system. I don't want the AI assist. 1729. Okay. The electrostatic phenomenon of attracting a small bits of matter could occur at one end of a damp string several hundred feet long. 60 years later, there was a short threads connected at one end to his primitive electrostatic machine became charged through their length, but no one deduced the concept of electrical transmission from this observation until after Gray's time. Okay, feel like we've been back through history, right? So now we go on and we go through and we say Volta and Oersted, and we twist and turn a little bit, and then we get into the underground cables, underwater cables, and all that kind of stuff. Okay. Then we get to Thompson. And again, I'm not going to expect this on a test or anything like that, but if you're curious, you can read through this and it's kind of see how we got to where we got. Now, in this period of time, there were some people that were doing some of this in the theoretically, and those people were the really big guns. And so this guy right here, the man chiefly responsible for new and more complete mathematical analysis of signal propagation on transmission lines, was Oliver Heaviside. Now, does anybody ever remember hearing of Oliver Heaviside anywhere else? Okay, he was the guy that invented Laplace transforms. Okay, so if you want to blame somebody for Laplace transforms, blame this guy. He was a recluse. Is the most unusual and at the same time most productive engineer mathematicians of all time. The nephew of Charles Wheatstone, a prominent electrical scientist and telegraph inventor, and brother of a well-known telegraph engineer, Oliver Heaviside worked for a few years in the British telegraph industry, then retired, according to Major Encyclopedia, in 1874 at age 24 to spend the next 50 years of his life in almost total seclusion. During that half century, his publication on transmission line, electric circuit theory, vector analysis, operational calculus, electromagnetic field theory, and numerous other topics did more to define the concepts and establish the theoretical methods of modern electrical engineering than as the work of any other individual. Transmission lines, as developed in several chapters of his book, is entirely the work of Oliver. Okay, so everything in the book that Chipman wrote was the work of Oliver Heaviside. And it was first published in the 1880s. Modern presentation of the Maxwell's electromagnetic theory are also essentially in the form created by Heaviside. Okay, so that's Heaviside. Historically very important. All right, so that's him. And then you get on in life, and you get down here and you say, okay, so who is Lee DeForest? An American. He invented the first, it was a diode or an amplifier. He did the first, it's called a triode amplifier. This is a tube type device that did what transistors do today, amplifier. Okay. And then after that came who? World War I, and things kept going. And then World War II. About that time, they also invented the ability to transmit with multiple frequencies, frequency jumping, and that was to fool the Germans because they had listened to them on a single frequency, but when you did frequency jumping, you can't listen to anybody because they're continually moving from frequency to frequency, so you can transmit without anybody seeing what you're doing. That was an American invention as well. Well, this is kind of historical, and I want you to know that it's here, and it's sort of like a walk through time to say that, this is not in your generation, but there were in your grandfather and maybe your great-grandfather's generation, a lot of this stuff actually was being invented. That was one of the things that got me when I was in school was 10 years before I was there, the guy who had invented the integrated circuit was at the same school doing the same stuff, so he was 10 years ahead of us. But anyway, integrated circuit was invented by a guy who invented basically TI, or Texas Instruments. I forget his name now, but anyway, he was the guy that invented the integrated circuit. So Maxwell's equations. What is Maxwell's equations? You don't really care, but I'm going to write them down so you at least have a reference for them so you know what they are. Not that you're going to use them in this class, but that they are what they are. So anyway, this is, there's two versions of Maxwell's equation. There's more than two versions, but this is what the heck did that do? Well, something happened. There we go. We're back again. Magic. So this is an integral form of Maxwell's equations. The integral around a surface of d dot ds is equal to q, which is also integral the volume of rho dv. And don't ask me what all these things mean because I'm not really familiar anymore with what they mean. Integral around a volume of E dot dl, that's length, L is length, equals 0. Integral around a volume of H dot dl is equal to I. That's I, which is what we know. I is current, which is equal to integral over a surface of J, which is current over a surface, dot ds. Okay, so H dot dl is equal to I, the integral of H dot dl. And the integral over a surface of B dot ds is equal to 0. Now that is the integral form of those puppies. The differential form of those, the point form. This is the integral form, and then the point form. This is the integral form. Point form, del cross E is equal to minus partial B partial T. Del cross H is equal to J plus partial D Ted over D partial T. Del dot D is equal to rho, and del dot B is equal to 0. Aren't you glad you asked? Now this was in a book that I took, I forget what the course number was, my first semester junior year, and it's by a guy named Hayt, H-A-Y-T. And I probably told you the story about this before, but I'll tell it to you again, bore you again. So I had gotten through 2 years of school, thought I was on my way, and I'd gotten an A in the physics course that studied about Maxwell's equation, or about equations like this and all this kind of stuff. And I just passed that physics course with an A, and thought I was in pretty good shape. So fall semester came around my junior year, and I wasn't clowning around, but I was pretty cocky. I thought I had everything in hand, and took test one. There were 4 tests, 4-hour exams. Took test one, and the 33 people in the class, or 32 people in the class in that range, I don't know exactly, but in the 30s, and they put the test scores up on the board after the test, and they handed it back and all that kind of stuff. Before we got our test handed back, they rolled all the scores down, and the low score was a 33, and I said, I wonder who the poor sap was who got the 33. And I got my test back, and it was me. And I gulped. I thought, what the heck is going on? And anyway, so I don't know, I just thought, what the heck is going on? So I stayed with it. Took test 2, so we're halfway through the semester, and I got a 57. Getting better, but still not passing. And somewhere along in there, it clicked in my brain that I wasn't studying right. And I don't know exactly why or how it came to me, but I said, I'm not remembering the steps to doing these problems on the test. And I analyzed that the problems that we were working were 7, 8, 9 step, 10-step problems. Step, 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 step. Make a decision, go this way, step, 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 go this way, whatever. So he worked all the problems on the board, just like clockwork. Everything got worked on the board, and I was so devastated. But I started looking at ways of remembering those, and I got little 3x5 cards, and problem on the front, solution on the back. And once we got a problem assigned, I'd do it in class, or I'd do it, look how they did, or whatever. And some things I did, some things I didn't do. But homework I was never really good at, but I tried my best, but sometimes I didn't get it. But anyway, when he worked it on the board, I copied it down and made note of it, then did it on a little 3x5 card, and then practiced these little 3x5 cards, not every day, but enough that I knew when the test came around how those decisions were. And the 3rd test I got in the 70s. I don't remember exactly what it was. The 4th test I got in the 90s. And I looked at it at the end, you take a final on this course, this book, and what the heck am I going to do? I'm going to get a C in this course even though I worked my butt off. And I got my grade back, and I got a B. And I went and asked the guy, I said, how did I ever get a B in this course? He said, well, you were going up, other people were going down. He said, you got right in the middle of the B range. I couldn't believe it. I could not believe that that was the way that the scores went. But it made me a firm believer in little cards. And it also made me a firm believer in points. What you get is what you get is what you get. It's not I like you or I like somebody else or I'll give you a bait favor or whatever. It's just grade on points, look at the scores, look at the lump sum at the end and take what you get. So again, I forgot everything that's in this book. I mean, I honestly, I couldn't remember these four equations if I had to. And that's not the point today, but I'm telling you that this, what we're doing right now is right down the pike of what I really suffered under as far as, it gave me confidence after the fact, but it was kind of a mess. So anyway, that's my story and I'm sticking to it. Okay, enough on that. Now, I wanted to go through and also talk about, and you can review this chapter, and there's two more chapters here as well. You can review this at your leisure, but I'm not going to go any further with the Chipman book. So again, I'm not going to do that. But I am going to talk about another chapter having to do with the stuff that's in these, which is the uh, the book on scan lecture material and the Sham E machine, chapter 1. Okay, this is something I want to talk about. And again, this is the stuff that we just looked at in those equations, the Maxwell's equations. And by the way, I'm going to lecture to you, but I've also asked some people from SSOE, and I don't know how many they're going to do, but you know, heaven help us, we're going to get through this. But I asked a lady from, what the heck is going on? Something I'm touching. Okay, I'm touching that. Okay, that must be it. But anyway, a former student here in EET land, and she is I don't know what her title is anymore, but the company is SSOE, and they're downtown, and they do automation like what I basically do, and then they also teach, they also not teach, but they also have a group of power engineers. And guess what? There are not enough of them to even come close to filling the need today. And what she said was, there is a great need today for power engineers. So if you're interested in a career, you know, I'd like to twist your arm and say, come on board with the automation side and do that. But I couldn't blame you at all if you wanted to go into the power side. So it's kind of like you have to choose your medicine, which way you want to go. You can't do both. You could, but it would be kind of lukewarm. You should go one way or the other. Decide I'm going to go into the power industry or I'm going to go into automation, one or the other. And those are two areas. And you may choose something else a little bit, but those are the two areas. But what they wanted to do, I could tell you, was to come in here and lecture and eyeball you and see who they would like to hire. Okay? So it's a chance for you to see them and for them to see you. So you don't have to wear a suit and tie every day, but I'm telling you that they're eyeballing you. If they do come in, and I think they will, I don't know exactly how many days they'll come in and do the lectures. But I asked specifically for a lecture on, or two or three, on the software for doing the big, like when I told you about a plant, how much current and where it goes and all that kind of stuff. That software, how that software works. In other words, bring your software in, show us how it works, show us how you do that, how you do. It's a load calculation type question, or how to, there's a one-line drawing for your plant. There's called a one line, and it shows you where all the power goes, and how to figure all the numbers on a one line, that type of thing. The other thing is how to find the short circuit current rating of a panel, SCCR of a panel. Now that may be easier, but I want to be able to, when you walk out of here, to know how to do that. Hopefully you will. Now I can dial up about half a dozen vendors and they all have their way of doing it with their equipment, but I would rather trust somebody that does that on a basis that does not necessarily just go to one vendor and say, how would you do it? So I would rather do it the other way. So anyway, SSOEs, maybe they're gonna come in, maybe they're not, but anyway, hopefully they do. If they do, I don't have to teach that day. I can sit and watch, just like I did during the labs today, where I didn't sit, I kind of fiddled around at other stuff, but my point is this, I'm not very good at this, and you can tell, but we'll try to enhance your abilities through other people, and if they come in and do, we'll clap and all that kind of stuff, but on the other hand, they're eyeballing you. They're eyeballing whoever they want to get and how they want to do what they want to do, and if they're interested, they may make you an offer you can't refuse. And by the way, what is it about power? I'm not against power. That's not my area of expertise, and it's not what I chose to do. But what is it about a power job? You make a lot of money and you don't get laid off. Why don't you get laid off? You're the only person who knows where the current goes. You're the only person that knows where all that current is going. And those guys do not get laid off. They can stay in a job for 40 years and not have to travel, not have to get on a plane, or not have to get their suitcase packed every Sunday night and come back on a Friday night, or any of that stuff. And they get to call the shots as to where things go and where the current goes. So anyway, you get a shot at them, they get a shot at you. Hopefully that's what happens. And if it does, it's, as I say, that's a win-win. Anyway, so this stuff here is, what is this? This is your B's and your F's and your all that kind of stuff. And this is kind of the stuff that we just saw with Maxwell's equations, isn't it? It's kind of that a little bit. Now, what is it about magnetism? Well, when you run a current through a wire, it creates a magnetic field. Sometimes there's not much current and it doesn't create much of a field, and you can ignore it, as in with low voltage, you can ignore it. But when you run a heavier current through a wire, it creates a magnetic field around it. Now that is a fact. And that magnetic field has some consequences to it. It can then induce a current into another wire further down the line or some other device. So you can get crosstalk. Now, this is all that oop-de-oop stuff in those Maxwell's equations. This is the equations, the basic, there is a thing called, the thing called resistance. Well, there is also a magnetic resistance. There is a Ohm's law. There is a Ohm's law for magnetic circuits. There's a current, and then there's a thing called flux. So the basic equation is between I and phi. Voltage, V, and the magnetomotive force, MMF, magnetomotive force. The conductivity, sigma, and the permeability, mu. The conductance, G, and the permanence, whatever that color is, whatever the guy is, I don't know. Anyway, but that's that. Now, I'm not going to make you do problems that's, in the past years I have, and I'm just not going to do that today, okay? Thank you, Professor Evans. What on earth? Let me see who this is real quick. Let's see if I can call him back. Okay, hopefully I can do that. So anyway, so you have these things called eddy current, and you have this thing called hysteresis loss. Now, what is an eddy current? What is an eddy? Daggone them. What on earth is going on? I didn't do anything this time. I didn't touch anything. What is an eddy? It's like this, isn't it? That's an eddy when it's like a swirl, that type of thing, okay? So if I have a signal, if I have a wire, it produces like a swirling current around, okay? Around, if I have a magnetic plate, there is a current that swirls around like this. If I induce a magnetic field here, it can swirl like that, okay? Now that can be good or it can be bad. If you use the circuit that actually induces this, you can do all kinds of things with it. For one, you can have a proximity switch, which is a barrel type switch. Prox switch, proximity switch, that can have a coil that induces an eddy current on a piece of metal. Then that eddy current can then induce a current back on a secondary coil in the same device. And that secondary coil, what does it tell you? If there's current, there's a metal in front of it. That's a prox switch. That's how prox switch works. So eddy currents aren't always bad. They can be bad, but they don't have to be bad. Okay? When you have a piece of metal in a furnace and you're inducing voltage and to try to get it hot, these eddy currents in the metal are what make it hot. So it's these swirling currents that make it hot. Okay? Now, why do we have laminates in motors? Here you've got if you look at the cross-sectional area of a field of a not a field, but the rotor of a of the rotor of a motor that's spinning. Here's your axle right there, and then you've got these long pieces where there's a metal with windings on it, and then you've got in between them you've got these pieces of insulation. Why do you do that? To cut down on the eddy current. Say if you have an insulator there, you can't have an eddy current except these little bitty ones. You can't have a big swirling eddy current. Now, all that said, and I may actually try to get this working one of these days and show it to you. Can you take a coffee can without any electrical connection to it and put it on a bushing so it'll spin? And can you put a magnetic field around it by little transformers and get this thing to spin? Can you spin a coffee can without touching it, is the question. Yes, you can. We actually got one upstairs, okay? That's like a motor, three-phase motor. We have a three-phase transformers that actually are around this, and they have a core. Each of them has cores in it, but we can actually take those 6 transformers around this thing and run a three-phase current through those transformers and get it to spin. And you say, no way. Well, we got the idea off the internet. We're not smart. We just looked at things on the internet, and they actually said, this is how you do it. We looked at it, and one of the capstone groups one time, they said, okay, let's do that. And they did, and it worked. It actually spins the coffee can. So in other words, even without any laminates, there's no laminates at all, you can still get it to spin. It's pretty weak. I mean, it's really, it's wimpy, really wimpy, but it does spin, okay? So even without the laminates, you can still get eddy currents onto this, and they're constantly turning, so they're pushing it one way or the other. Now we can even with this thing if you take three-phase to a motor, and if you turn any two wires around, what do? You reverse the motor, don't you? You reverse the direction of the motor. We can even do that with this. You have it spinning to the left or counterclockwise. Take any two leads, turn them around. In other words, flip them, and it'll spin the other way. And you don't believe that? We'll try it. It'll work. You'll see it, okay? So we're going to set that up upstairs. Not today, but one of these days we'll set it up. And I don't know if it'll be during lab or during lecture or whatever, but you'll actually see that happen. So eddy currents, this has got eddy currents all over the place, but at least you now know that you can still get some of the same result even though with those laminates. Okay, so again, sometimes eddy currents are good, sometimes they're bad, and you can use eddy currents as well for metal detectors, walking into an airport, that type of thing. When you're walking into an event where they make you walk through something, that's the same thing, and they're looking for that eddy current spinning of that current on a device that might be metal, probably is metal, that type of thing. Okay, the old ones were less sophisticated than new ones. I don't know all the stuff they do with the new ones, but the old ones, if they're cigarette packet, that was one of the biggest ones. Belt loops, I don't know all the stuff they do anymore, but anyway, the old earlier ones basically were just looking for eddy currents. That's what they were, that's all they were looking for. So they were doing this kind of thing, the proximity switch trick, but they induced around you, and then they were picking up a signal back from that eddy current that was spinning that would actually send a signal back to their secondary coil. Primary coil generates the eddy current. Secondary coil sees the eddy current feeding back to a secondary item. Okay, so that's that. Hysteresis loss. Now, what is hysteresis? It's a lag, isn't it? You set those electrons up with them in a magnetic circuit. Why do motors use iron? It's got a memory. Those little electrons in iron, they're spinning, and they don't immediately flip over to do something else. Why don't they use something like copper or silver in a motor for the iron instead of the iron? You wrap a coil of wire around an iron core. Why do they use iron? Because it's got hysteresis. Okay. If you wrapped a coil of wire around a copper, it doesn't have the hysteresis. It doesn't remember those electrons weren't setting spinning, and then they remain setting spinning even after you turn it off for a little bit, not forever, but there's a little bit of a lag. In other words, that lag is what you're actually allowing to use to push the motor around. You're constantly changing where your north and south pole are, and the lag of their spinning, they still want to spin the same way that they were spinning, and that's what you're actually pushing against. So again, it's the hysteresis of the motor that allows the motor to work. Okay, now there's a laminate, there's a non-laminate. Now what am I getting to? Well, I'm saying that there is a good and a bad about this magnetic field in a circuit. And you can use this to do all kinds of things. For instance, you can use a magnetic circuit, a magnetic field, to trigger a relay. And I just brought along some relays. I brought a bunch of relays on. This is a relay. So you can actually energize it, and it'll turn on, and it'll energize, okay? Now I have a little one here that is a little toy one. It's just a little bitty one, but you can actually see it here, and there's the coil of it, and you can touch this, and you can see it actually turning on, and it turns on that contact. It makes that contact change. So I'm going to pass this around so you can. What you got to do? The coil is between there's pins down here, and then there's two pins up here. The two pins up here are the coil, and you've got this is the plus and the minus 9 volts. That's a 12 volt, but it'll still work at 9 volts. You touch it between those two, and you'll actually see it change. You can hear it too. I'll pass that around. So you can use a magnetic circuit to move, actually do some work, and that's what that is. Okay. So that's that one. This is a machine tool relay, and this you energize it and it pulls in. And I'm going to do another one here that's perhaps a little bit, oh, you can hear this one. Actually, hear this one coming in. So this has got a coil in there, and you can plug this in and you can see it, you can hear it. Okay. And if you want to, you have a, you don't have 10 volts. Yeah. Anyway, if anybody wants to play with this afterwards, they can. So there this is. This is the same relay. Here's the coil of it. So this is a relay we just had. There's the coil and there's the core. And why is it iron? Because it's magnetized. You can let's put this together. Anyway, this is the top part. There's that. There's a bottom part to it as well. Someplace in here. Here's the bottom. Here's the bottom part. That sits like that. It sits right on it. Okay. So okay, so we've got this idea of a magnet, and it can turn something on. Now, why is this important? Well, something very practical is a solenoid. That's what I was looking for a little bit earlier. Solenoids are like relays, except for the fact that you don't have contacts with them. So if you have an armature that you want to move one way or the other, but you don't have a contact associated with it, that's a solenoid. Okay, so just move back or forth. It's got a spring on one side, and it's got a magnetic coil that you can actually make it energize it, and it'll move one way, de-energize it, and it moves back the other way. So that's just an arm that goes back and forth. Okay, so and they don't go very far, maybe half an inch or quarter of an inch or whatever, but that's what a solenoid does. It moves a little arm back and forth. Okay, so what do you use these little guys for? What do you use solenoids for? Well, how about to move a gate on a piece of equipment, so it'll go one way or the other. Okay, to move a gate. Let's just say that would be one thing you could do with it. Okay. Okay, so moving a gate. I think this thing's just going to whatever to move a gate. Okay, so move a gate. Okay. So that would be what the solenoid could do. It could move a gate back and forth. Okay. Now you say that's nice. All you got to do is turn it on and turn it off, right? That's about it. Well, not really, because you have to think about it for a little bit. And this thing, when it turns on, what does the current do? So if you look at time and you look at current, what does the current do? It does something like this, and it comes back like this. Now, why does it do this bump at the beginning? Well, when there's a big gap between where it's going and where it ends up, there is a high current required to energize that relay. In other words, to energize that circuit, it takes a lot more current. When there's a large gap, there's a lot of energy required. When there is a small gap, there's less energy required. Okay? So with a solenoid that is used in industry, this is about 3 times this number right here. So if this was, let's say this was 0.2 amps, this would be about 0.6 amps. So it's about 3 times. This height is about 3 times that height, roughly. Does that matter? It can. Okay, so when something is open, when it closes, there's a low current draw. When it's open, there's a high current draw. All right, so you see that difference. Now, what does that mean? Well, if you size your wire to this, it might work, it will work, but but you have to start it with this. So you have to size your wire to the starting current, it'll never work if you don't get it. If you don't get over that hump, it'll never work. Okay, does that make sense? So here's the deal. This is the Owens-Corning rule of thumb. If you have a solenoid and you want to run it more than 200 feet, use number 12 gauge wire. Less than 200 feet, use a 14 gauge wire. We used 14 gauge wire for everything, pretty much. But if you go beyond 200 feet, now why would that be a situation? Because what does the current have to do? It has to go out to the solenoid, and the symbol for solenoid is this little device like that. Then you have to come back, don't you? You have to go 400 feet. That's 400 feet. And then the ohms per foot, where do you get that from? Get from National Electric Code, don't you? Okay? The National Electric Code says so many ohms per foot for a 14 gauge or for a 12 gauge. And now if it takes 90 volts for this to turn on and you start with 110 volts, you can't lose more than, okay, so you started, if you started 100, if you have 110 volts here, you need at least 90 here, so you can't lose more than 20 volts. And that current times that ohms per foot gives you the amount that you can actually drop. So in other words, we really didn't care. You just had to know that if you were under 200 feet, you could use 14 gauge wire. But the reason that you could use the 14 gauge wire was because the ohms per foot was sufficient that you could, if this turned on at 90 volts, after it turned on, you didn't care because it was down here. But you see, the actual magnetization force is this current right here. That's the current that's going to get you. And if you can't get it started, then you can't be able to ever turn on. And that mistake was done many, many, many times, that they would have to go back and pull a heavier gauge wire because try it and turn it on, wouldn't turn on. Why not? Well, you went too far, okay? Any questions about that? That's as much as I'm going to say about chapter 1. But the B that you're going to see, the actual, the magnetization force that you have there, the B force, is you got to have enough to get over this hump. And you got to furnish enough current to do that. In order to do that, you have to go to a bigger size wire many times, and that's why. Okay? Again, that is a very practical application of this concept. All right, now another one. What on earth is going on? Well, here's another one. Something is not working.
It seems like when you hit
What's that?
new notepad, it
It,
updates the resolution or something and just refreshes.
all right, well, okay. It comes back on when I hit new, that's it? Okay. So now I've got two solenoids. I've got one that wants to go this way and one that wants to go this way. Now, can you think of any situations like that? What about a latch relay? Okay. Now, in essence, what a latch relay is, it's a switch that will set in a position. And I don't have a switch over here. I don't have a switch anymore. But if you had a switch, you'd actually push, one would be idle, one would not be pushing, and the other one push it up, and then the switch would be in the up position. The other one would be idle, and the other one would be pushing in the down position, right? So what happens when you have both of them pushing. You have this current, this higher current in both of them. And that's why it's like two sumo wrestlers that will not, that they're locked in a death grip. And one of them is going to die. Not really die, but he's going to give up. But in a latch relay, if you have a latch circuit with a latch relay, you must design it so that you cannot turn both of those turn on. You cannot turn both coils on at the same time. If you do, one is going to burn up. The weaker of the two is going to burn up. It's going to sit there, high current, high current, high current, not designed for high current indefinitely. And your current is going to heat the thing up until it burns it up. So again, latch relays in a PLC, you have to worry about because you can't burn up a bit in a PLC. But a real latch relay, you have to design it so that one of these turns on, but not the other. Only one. You can't have both on at the same time. Or else you bought the farm. Literally, you bought the farm. You cannot, or does that make sense? So it's another case of this idea of this higher, with a bigger gap, it's trying to narrow that gap down to nothing, okay? So if it narrows it down to nothing, there's a lower current rating. You can get your magnetic field with a lower current rating. But if it's got a big gap, an air gap, a large air gap, then high current. And if they've both got that high current, one of them's going to lose, and one of them's going to burn up. Okay. So what else have I got? What other tricks do I have up my sleeve today, huh? Well, I have for you, and this is something that we can put on a test. This is something that we can actually test you on, and not as opposed to other stuff, which is kind of, we're just talking through this stuff. But ECNM, and I want you to join this. This is kind of a, a free swing type stuff. But ECNM is a website. Come on, Ted. ECNM, Ted. ECNM. There you go, finally. Okay, so you have to be a member. So I just signed up back. I signed back up for this after years of not. I used to do this all the time. Why would I do this? They have these quizzes. Okay. This is what I want you to do. This is your first assignment. And I know they give you the answers at the end, so you can, all you gotta do is go through it. It's not a big deal, but here they are. Okay, so let's go through this. And I know it says per the 2023 code, so you have to know the code book a little bit in order to do this. But I'm expecting you to either maybe buy a copy of the code book or at least take a swig at it or swing at it to see if you can come up with it, okay? So, members only quiz. This is not the same one. This is it. This is the one I wanted you to, this is the one I wanted you to look at. Grounding and bonding requirements per the National Electrical Code. Okay? You're gonna love these. Some of them get wild. What is the effective ground fault current path? Any ideas?
Yeah, C,
Anybody else?
B,
Huh?
B, the second one.
B, yeah. I think that's right, yeah. What's the second one? Why is the Earth by itself not considered an effective ground current according to the NEC? Hmm?
Because it has high impedance.
I think so. Is that, anybody else, what do you think? B? See, we'll get the answers at the end. Okay, next. What will be the maximum fault current when there is a 120 volt ground fault to metal parts of a light pole grounded to a 25 ohm ground rod, but not bonded to an effective ground fault current path? Okay, 125 volts, 25. Is that 120 divided by 25? Is it B? I'm not done this. Is that right?
Yeah.
That's right. You see what this does? It humbles anybody. It humbles everybody after a while because you're not smarter than these guys. They're pretty daggone whatever. Okay, 14 types of things you can use as an EGC. What is an EGC?
Road grounding.
Yeah, some kind of a conduit. Okay, so which of the choices specifically prohibited by section 250-118B? I would say gutters, but I'm not sure. What do you think? Anybody else thought of anything? Probably, like B is a prominent answer here. Okay, metal raceways, cables, and enclosures that could become energized must be installed in a manner that creates low impedance circuit to facilitate the opening of the OCPD. Which NEC requirement supports this statement? I have no clue.
That was,
Huh?
I think it's
C? I was trying, I don't care. Some of these I'll never ask. Okay, would you like to be entered in a contest? No, I do not. See results. Let's see what the results is. You results 60%. So we got 3 out of 5. Okay. See what everybody else got. Average score is 68. Hey, we're close. Okay. Any questions?
The actual answers answered.
How do you compare? Take the quiz again. Here's a correct answer. We were correct on 1, correct on 2, correct on 3, not correct on 4. Grounding electrode conductors, and then number 5, we just take a swag at that. So anyway, any questions about that? If we had a copy of the code, we could have gotten 5, and we could have gotten 4. So again, if we had a copy sitting here, we could pull these all together, and we could have done these. We could have won out. Okay. So I want you to hand something in. So by next week, I want you to, print that out or whatever and give me those 5 answers. You can get 100% on that, and we'll go on. But every week they have one a week, by the way. That makes it easy. And those are good test questions, and those are questions that I can't ask you on. So I feel like that is something that, even though you can bring with you a paper that will answer, you can have the answers on a piece of paper and all that kind of stuff, but at least it gets you savvy. It sharpens you up tremendously if you do this on a continuing basis. You cannot take this and not feel humbled, and in the same breath, you can actually learn a lot. Okay, learn what they're thinking. Okay, enough on that. Anybody have any questions? Let's see, I'm done today. Take care. So that's your assignment. That'll be posted. That was your assignment.